Okay, so if you have worked out reflection and transmission at normal incidence, then you'll feel even more rewarding after working through, reflection and transmission at oblique incidence. So now we have the propagation direction that's no longer normal to the surface, and then we have reflection and we have transmission. So this become more complicated. So why do we have scenarios like this? For many optical devices, we want to steer, light signal, optical signal towards a desired direction, and we want to be able to control how much percentage of reflection and transmission we want to create in different media, and especially for fiber communication. We first need to we have a fiber. We first need to get light in, and then we need to ensure that light would propagate down the fiber, down the wire. But it's not like shooting a bullet into the fiber and then it just goes straight down. It's not like that. We need to find the angle that we have the total transmission. So light does get in the medium. And then inside the medium, we need to design in a way that we have total internal reflection. So there is a medium of, fiber core and cladding. So we want to contain light within core so that it keep propagating down the wire. So we need to ensure that the angle inside the fiber, all the reflection angles inside the fiber would have total internal reflection without light escaping from the core. So this is a very important issue, but we can still approach this step by step, similar to what we have done before. So let's first of all clarify let's first of all extend the expressions for wave functions. So we have wave functions. So the first case, which is the most simple case, is that for the electric field, we would have X polarized. So X polarization, but we have Z as propagation direction. So this is the most simple case. So if you have look at here, so we have the propagation direction, and then naturally electric field is perpendicular to the direction of travel. We have E, I, complex value, and vector. However, if we have normal propagation direction, and then the polarization is towards X direction, in the X direction, that would make the wave function very easy. So we have the input, we have the incident wave with EI equals to E0, the amplitude, and then complex value amplitude, and then propagation function I, kappa 1, Z minus omega t in the X direction. So for medium 1, we always have a set of parameters, permittivity, permeability, and then wave number, and then index of refraction. And then for index 2, we have different set of parameters. We have epsilon 2, mu 2, kappa 2, and then n2. So the incident light would have, kappa 1. So this is the most simple case where we have the polarization in the X direction. So now the B field, we have 1 divided by V1, and then propagation direction cross electric field. So we would have 1 divided by v1, and then the amplitude, and then propagation function, kappa 1 z minus omega t, and then y direction. So this is the most simple case. So if we have an extension from here, we can still propagate down in the z direction, but the polarization direction could be a phase rotation to x. It doesn't have to be, you know, straight x direction. It could be any direction on the xy plane as long as it's still perpendicular to the propagation direction. So the second case, we have you know, we relax this condition. We have propagation direction is z direction. So propagation. Then we have a more general expression here. We have EI equals to a polarization vector, and then propagation function. We can see that this x direction is absorbed into this polarization factor. So this polarization, this is a propagation function. We look at them separately. The polarization is a complex value vector. So we have x component, y component, but it is a constant. It represents our message. Once we decided what message to transmit, then the message shouldn't change over distance and time. And then propagation function is a scalar, but it's a function. It's a scalar function. It would vary with the distance and time. So now the B field would equal to still 1 divided by v1, and then propagation direction is still z, and then cross the electric field. Okay, so third case, would be even more general. So if I have any direction, so the propagation direction is no longer restricted to, you know, z direction. In this free space, any direction is possible. So we denote that direction by kappa I. So here we have the propagation direction is z. So if you assign kappa 1 to be kappa I to be a vector, then dot product between, you know, kappa 1 vector and z direction would be just the multiplication between the two magnitudes. But now if the propagation direction can be any direction, then we use this vector, this wave vector, to indicate the direction of propagation. So we have any propagation direction indicated by kappa I. So naturally you have kappa I. The amplitude is kappa 1. The direction is indicated by kappa I unit vector. Okay. So now we have a more complicated expression. We have the electrical field EI would equal to the polarization vector, and then the propagation function, which is I, and then kappa I dot a position vector minus omega t. So originally the position is anywhere on the z direction because that's a propagation direction. But now we use a position vector. So basically, when the position vector that you are calculating is in the same direction as the direction of propagation, then the dot product would achieve the maximum. But don't worry too much about this. We are going to use some basic laws to help us to get rid of this, so that our calculations are still based on a phase rotation to x direction, phase rotation to y direction, and phase rotation to z direction. We wouldn't be dealing with r directly. We want to simplify this. Okay, so magnetic field, we have BI equals 1 divided by V1, and then kappa I unit vector, the direction of propagation, cross E field. Okay. So we want to simplify this. We don't want to directly deal with a variable vector. We want to deal with a coordinate with x, y, z. So the direction could be expressed as x, y, z with phase rotation. So we need some help. We have 3 fundamental laws of geometrical optics, which are actually quite simple. You have heard of them before. So I have 3 fundamental laws of geometrical optics. So the first law is about plane of incidence. So it says that the wave vectors kappa I, kappa R, and kappa T, they define a plane. So kappa I, kappa R, and kappa T form a plane. So why is this helpful? So we have this reflection and transmission in 3D. So the x, y, z coordinate could be anything. You can rotate it yourself. But we want to set the x, y, z coordinate to be convenient for calculation. So if the 3 wave vectors they define a plane, we might as well define this plane as xz plane. So we may, for the sake of convenience, we normally define the normal to the surface z-axis, and then the normal to the axis along the surface x-axis. So roughly, the propagation direction is some phase rotation to the z direction, and then the polarization of the electrical field is some phase rotation to the x direction. That's close enough to the coordinate that we are familiar with, especially when we did the normal incidence. So now we can pin down more parameters. So here we have the incident wave. So the electrical field here, the direction is some phase rotation to x, and then the magnetic field direction here, based on right-hand rule, it will be pointing out of the plane, which is y direction. So here, the magnetic field direction would be pointing out of the plane, which is y direction. And then the angle here, angle of incidence, we have theta I. And then for the reflection, we have the electric field perpendicular to the propagation direction. So here we have ER. And then the magnetic field here, right-hand rule, we have propagation direction and then the electric field. So the magnetic field is pointing into the plane. So I have the magnetic field here is pointing into the plane, which is minus y direction. So this angle here, we can define as the angle of reflection. And then the transmission, we have electric field pointing this direction, so I have E T. So based on right-hand rule here, propagation direction and then electric field, the magnetic field direction at this point is perpendicular out of the plane. So we have, the magnetic field here, direction is pointing out, which is y direction. And then this angle, we can define this as theta t, so transmission angle. So now we pin down more parameters, all because of the first law. And now the second law. It's about reflection. You probably know this from kindergarten. Actually, we have the reflected angle equals to incident angle. So basically, when you did, this science experiment of bouncing a ball off the ground, you will observe that the reflected angle equal to incident angle. So that's also quite simple. And the third one is also very simple. We have the third law, that's about refraction, transmission. Third law, we have Snell's law. This is about refraction. So basically we have sine theta t divided by sine theta I equals to n1 divided by n2. So basically the relationship between theta and theta t is determined by the medium parameters. So if we extend this a little bit further for the sake of calculation, we know the definition of n equals to c divided by v. So n is inversely proportional to v. So this also equals to v2 divided by v1. And we also know that the angular frequency equals kappa v, or we can write this as v equals omega divided by kappa. So on the two sides, the oscillation doesn't change. which means the angular velocity doesn't change. So I have kappa inversely proportionate to v. So I have kappa 1 divided by kappa 2. So this would be helpful for our calculation later. Okay, now we are able to fully draw this diagram with the aid of the 3 fundamental laws of geometrical optics. So the next task is to write out the wave equations for all of them. So actually still the most important wave equation is EI, and then all the others, they are in similar forms. So we can write all the wave equations down and then check if they are in a similar form by replacing, amplitude. Here we have E0, and then here we would have RE0. So a percentage of the wave would go to reflection. That percentage is represented by R. And then here we have TE0, which is, T is the percentage of the wave to transmission. And after we express this, we replace, theta I by theta R for ER, theta I by theta T for ET. So anyway, let's look at them in detail. It's really, really possible. It's not that complicated. It's nothing. It has really nothing to do with calculus, but a little bit more on linear algebra. So we have to work out all wave functions. So first, for the incident wave, this is the most important starting point. Incidence. So here, the polarization of the E field is this direction. So, which means the polarization of E field would have some component, some horizontal component, some vertical component. So if we draw a line that's parallel to the surface, so here we have theta I. This angle is also theta I. So now we know the vertical component would be EI cosine theta I, and the horizontal component would be EI sine cosine I. So that makes it a lot easier. So EI. So first, the polarization, we have the amplitude is E0, and then cosine theta I, x direction, minus E0 sine theta I, y direction. So the vertical component is EI cosine I, E0 cosine I, x direction. And the horizontal component is pointing to minus z. Oh, sorry, here it's z. I have z direction. Okay, so that's the polarization. And then we have the propagation function. So for propagation function, we are looking at this wave vector. So this wave vector would have vertical component and the horizontal component. So for this wave vector, the vertical component is kappa 1 sine theta I. And then the horizontal component of this vector is kappa I cosine theta I. So now we have, for the propagation function, I have EI. And the x component is here. And then sine theta I. So here, sine theta I. We have kappa 1 sine theta I x. And then the vertical component for this vector is horizontal component is kappa 1 cosine I. So we have kappa 1 cosine theta I z, and then minus omega t. Okay. So be careful that this vector and this vector, they are two separate things. So this vector would have horizontal component and vertical component, and this vector would have horizontal component and vertical component. They are not the same thing. Okay, so we have EI and then BI would equal to 1 divided by V1, and then propagation direction Ki cross the E field. So magnetic field is always quite easy to write. We have 1 over V1, and then E0. And then propagation function is the same, which is EI kappa 1 sin theta I x plus kappa 1 cosine theta I z. Yes, and then minus omega t. Okay, so that's the incident wave. Similarly, for the reflected wave, we draw a line that's parallel to the surface when we try to express, the polarization here. So this angle is equal to theta r. So I have the vertical component would be the amplitude of ER cosine theta r, and the horizontal component would be the amplitude of ER sin theta r. So the amplitude of ER is R E0, so R ratio R of the incident wave. So I have ER equals to R E0 cosine theta R x direction plus R E0 sin theta r z direction. That's a polarization. And then the propagation direction, we observe this vector kappa r. So we have the horizontal component, which is kappa 1. So kappa 1 cosine theta r, and then the vertical component is kappa 1 sin theta r. So vertical component is x, so we have EI kappa 1 sin theta r, and then the horizontal component is minus z, so we have minus kappa 1 cosine theta r z minus omega t. Oh, I forgot something. So for the B field here, the direction is perpendicular out. So I have y direction. Yes. Okay. So now the B field is always very easy after you finish the electric field. So this is 1 divided by V1. And then kappa r direction cross ER. We know this direction would be minus y direction. So we have 1 divided r divided by V1, and then E0. And then propagation function is the same as this one. We have I kappa 1 sin theta r x minus kappa 1 cosine theta r z minus omega t, and then direction is minus y, so y minus, let me check, yes, that's no problem. Okay, so for the transmitted wave, if we draw a line parallel to the surface, this is theta t and this angle is theta t. So it's quite easy to see the vertical component and the parallel component. So for the transmitted wave, we have Et equals to, so the vertical component is the amplitude multiply cosine theta t. So we have TE0 cosine theta t x direction. And then the horizontal component is the amplitude sine theta t, but opposite to the z direction, so minus z. So minus TE0 sine theta t z direction. Yes, so that's a polarization. And then propagation direction, we observe this vector kappa t. So the vertical component is k2 sine theta t. We have ei kappa 2 sine theta t x. And then the horizontal component is k2 cosine theta t. So we have positive k2 cosine theta t z minus omega t. Okay, and then the magnetic field 1 divided by V2 now, the second medium, and then kappa t cross the electrical field. We have the direction we know is going to be y direction. This equals to t divided by V2 E0. And then the propagation function is the same. Ei kappa 2 sine theta t x plus k2 cosine theta t z minus omega t. Direction is y. So it seems very complicated, but actually all the electrical fields, they are in similar format, but we need to replace some parameters when we compare the two every pair of electrical field. So for example, from here to here, obviously we need to replace E0 by R, E0, theta I by theta R. And in terms of direction, polarization direction, we have the minus z direction, and here we have positive z direction. So we have positive z direction. And then in terms of propagation direction, here we have positive x and positive z. And here we have positive x but negative z. So we replace z by minus z. And that's about it. So from here to here, we need to replace R, E0. And then the polarization direction, the sum of the polarization direction here is minus. We need to have positive polarization direction. And then propagation direction from here to here, we have the positive change to negative. You can read them from the diagram. So after you finish this, you replace these parameters, then you get the second wave. Oh, and also the theta I must be replaced by theta R. And similarly, we have from here to here, from here to here. So first of all, the amplitude must be replaced by t E0, and then obviously theta I must be replaced by theta t, and then the polarization direction, the sign of the xz, they will be the same. Propagation direction is the same as well, right? Yes, the same as well. So this direction, this vector, these two vectors, they will have the same sign for the x component, same sign for the z component. In terms of propagation, also they would have the same sign for the x direction and the same sign for the z direction. So other thing to replace would be kappa 1 must be replaced by kappa 2. Kappa 1 must be replaced by kappa 2. And then V1 must be replaced by V2. So here V2, V1. So if you replace all of them, you'll see the connection between pairs of electric field. Let's summarize this kind of replacements in wave functions neatly in a table. So we have EI, and then we have ER, and then we have ET. So first we have amplitude. For the incident wave, the amplitude is E0, and this needs to be replaced by R E0 for the reflected wave, and the T E0 for the transmitted wave. And secondly, we have the angle. So the incident angle is theta I, and in the wave function, we replace theta I by theta R for the reflected wave, and then we have theta T for the transmitted wave. And then another thing is wave number. So kappa. So we have kappa 1 for incident wave, kappa 1 for the reflected wave, and then we have kappa 2 for the transmitted wave. Next, we have signs of polarization. So Z. So polarization, these 2 points to the similar direction. They would have the same sign for the X component, Z component. But this one would have different sign for the Z component. So the sign of, polarization, component Z. So we have, so here we have negative Z. And then here we would have positive Z. So we will have positive Z. And then here we will have negative Z again. And finally, we have the sign for the propagation direction, especially for the z component, actually just for the z component, because all of them have positive, all the wave vectors, they have the same sign for the x direction, but these two would have the same sign, positive sign for the z direction. Reflected wave would have negative sign for the z direction. So we have positive, negative propagation direction. So here, the first one we have positive z. Yes, positive z. And this would have negative z component. And then this would have positive z component. So actually, after you write out the first wave function, you can replace all these parameters by all these parameters, and then you get the electric field for the reflected wave. And then you use this set of parameters, you get the wave function for the transmitted wave. So the first one is the most important one. All the others, they follow similar rule, and you can check by yourself whether you make all the functions correct. Okay, now we're ready to solve all the wave functions based on boundary conditions. So we have some preconditions based on the three fundamental laws. So three fundamental laws, let's write it down here. So I have preconditions. So the second law of reflection, reflection tells us that theta I equals theta r. And then the third law of refraction tells us that sine theta t divided by sine theta I equals to n1 divided by n2 equal to v2 divided by v1 equals to kappa 1 divided by kappa 2. So we would have kappa 1 sin theta I equals to kappa 1 sin theta r, because theta I equals to theta r, and this would equal to kappa 2 sin theta t. Okay, so now we are ready to check the boundary conditions. So the first condition is epsilon 1 E1 normal component equal to epsilon 2 E2 normal component. So what does this mean? So if we look at here, so for all the E fields, the normal component is the Z component, the polarization Z component. And on the left-hand side, we have EI, ER. On the right-hand side, we have ET. So basically, here we would have epsilon 1 EI plus ER. We have their polarization Z component. We also have the variable Z equal to 0 for the propagation function. So the location of the boundary is Z equal to 0 for the propagation function, here, here, here. And the normal component is this one, Z, Z, Z. It is a polarization Z. So not to confuse these two. So we have Z component for polarization and the variable Z equal to 0 for propagation function on the left-hand side. And then on the right-hand side, we have epsilon 2 ET. and then polarization z component, variable z equal to 0. So what does this mean? So if you look at the normal component, so the 3 electrical field. So first we look at the propagation function, which is very easy to see because so here we have the precondition k1 sine theta I equals to k1 sine theta r equal to k2 sine theta t. So we have this term equal to this term and equal to this term. And then we have z, variable z equal to 0. So this term, they are all 0. Omega t, they are all the same. So on both sides of the boundary condition, the propagation function, we don't need to care about it anymore. They are all cancelled. Okay. And then the normal component is the z component for the polarization. So we only care about the z direction. And then for the z component of the polarization, E0 can be cancelled. So we would have epsilon 1 minus theta I plus r sine theta r. Sine theta r is theta I as well. Theta I equal to theta r equals to right hand side theta 2 multiply minus t sine theta t. So this boundary condition leads to a very simple relationship, which is epsilon 1 minus sine theta I plus r sine theta I. So this is actually sine theta r, but sine theta r equals to sine theta I on the left hand side. So this equals to epsilon 2 and then minus t sine theta t. So this is quite neat. We have relationship between r and t. So if we have another relationship equation for r and t, we can solve r and t. So now let's check the second boundary condition. We have B1 normal component equals B2 normal component. This is actually trivial because B doesn't have normal component. So so the direction of B field is always either y direction or minus y direction that is parallel to the surface. B field, all the B fields, they don't have Z component. So this is trivial. It doesn't give us any relationship. We only have 0 equal to 0. And then third, third boundary condition, we have E1 parallel component equals to E2 parallel component. So for all the electrical field, we have X component and Z component. So Z component is the normal component to the surface. And then X component is the component that's parallel to the surface. So this boundary condition means we have EI plus ER on the left hand side. Parallel component, we care about X direction for the polarization, and then variable Z equal to 0 for the boundary, at the boundary. This equals to E T X component for the polarization as well, and location Z equal to 0. So for all the 3 electrical field, if we only care about the X component, so propagation functions, they are all cancelled. And then X component, we have E0 cosine I. Here we have R, E0 cosine R. Cosine R is equal to cosine I. And here we have T, E0 cosine T. So we cancel all the E0. We get another very neat relationship as well. So we have cosine theta I plus R cosine theta I equals t cosine theta t. So now we get another relationship between R and T. Let's still check the last boundary condition, which is 1 divided by mu1 B1 parallel component equals to 1 divided by mu2 B2 parallel component. So B parallel component, so B field is either positive y or negative y direction. So B field is naturally parallel to the surface. So if you look at all the B fields, the propagation function, they can be cancelled as well. So on the left hand side, we have 1 divided by V1 minus R divided by V1. That's quite neat. And then on the right hand side, we have T divided by V2. So E0, the same amplitude, can be cancelled as well. So anyway, so this means that we have, on the left hand side, we have BI plus BR. We care about the y component that's parallel to the surface, and then at the surface, variable z equal to 0 equals to BT y component z equal to 0, and this leads to 1 divide, on the left hand side we have multiply 1 divided by mu1, and on the right hand side we have 1 divided by mu2. So now we have, on the left hand side, we have mu1 v1, and then 1 minus r equals to 1 divided by mu2 v2 t. Okay. So now let's define a parameter to help us to summarize all these relationships. So first, based on this, we want to define a beta equals to mu1 v1 divided by mu2 v2. So this would be beta if you move mu1 v1 to the right hand side. And then because n equals c divided by v, so n is inversely proportionate to v, so we have mu1 n2 divided by mu2 n1. So that's going to be helpful to us at some stage. And then also we have, because v equals 1 divided by mu epsilon square root, so we have mu v equals 1 over epsilon v. So this here we can also express this as epsilon 2 v2 divided by epsilon 1 v1. And v and n are inversely proportionate to each other. So here we have epsilon 2 n. So epsilon 2 n1 divided by epsilon 1 n2. Yes. So now we are ready to look at summarize all the boundary conditions. So for the first one here, the first boundary condition, we have, so epsilon 1 minus r equals epsilon 2 t. So if you move sin theta I to the other side, we have n1 divided by n2 equal to sine theta t divided by sine theta I. So theta I down here. So we have epsilon 1 minus r equal to epsilon 2 t multiply n1 divided by n2. And then epsilon 2 n1 divided by epsilon 1 n2 would give us beta. So this gives us 1 minus r equals to beta t. And then the last boundary condition also gives us the same. So the last one also gives us 1 minus r equals beta t. So this is a very neat relationship between r and t. So another one we are going to use is this one. So let's define another parameter alpha equals to cosine theta t divided by cosine theta I. So I have the third boundary condition. So this becomes 1 plus r equals alpha t. So now based on these two, we would be able to express r and t as function of alpha and beta. And alpha and beta, they are only about, beta is only about the material, alpha is only about the angle that we point to the surface. So from these two, I have 1 plus alpha divided by 1 plus r divided by alpha equal to t, and this equals to 1 minus r divided by beta. So basically r equals to alpha minus beta divided by alpha plus beta. And then t would equal to 1 plus r divided by alpha. So this equals to 2 divided by alpha plus beta. Okay. So actually this leads to the famous Fresnel's formula. We also often call it Fresnel's equations. So basically we have r equals alpha plus beta, alpha minus beta divided by alpha plus beta. And then we have t equals 2 divided by alpha plus beta. Okay. So in terms of amplitude of the wave for the incident, reflected, and transmission, we have amplitude of the reflected wave would equal to r E0 in. So we have alpha minus beta divided by alpha plus beta, and then E0 I, incident and reflected. And then we have E0t equals t E0 in. So we have 2 divided by alpha plus beta, and then E0I, where alpha equals to cosine theta t divided by cosine theta I, and beta equals to mu1 n2 divided by mu2 n1. So if Maxwell's equation is at the center of electromagnetism, then Fresnel's equations is at the center of electromagnetism for communications. So this tells us the relationship between incident wave amplitude and reflected wave amplitude. Incident wave amplitude and transmitted wave amplitude. So let's look at some special cases. So alpha here can also be expressed as alpha equals to 1 minus n1 divided by n2 sine theta I square, and then square root of the whole thing divided by cosine theta. So this is cosine theta t, and then we use 1 minus sine theta t squared, and then we call it Snell's law. So we get this alpha. So now we can observe that when theta t theta t here equals to 0, theta t equal to 0, we have, theta I equal to 0. Yes, when theta I equal to 0, we have normal incident. So when theta I equal to 0, let me check. Yeah, when theta I equal to 0, then here we have 0. So here we have 1, here we have 1. So we have normal incidence where alpha equals 1. So this is 0 degree, this is 0 degree. And then this is 0. We have 1 divided by 1. Alternatively, if I have theta I equals pi over 2, what do we have? So pi over 2 will make alpha equal to infinite. When alpha equal to infinite, t equal to 0, r equal to 1, because here we have 1 minus beta divided by alpha. Here we have 1 plus beta divided by alpha. So r equals 1, t equal to 0. So we have total reflection. In the third case, what happens when I have alpha equals beta? Then we have r equal to 0, we have total transmission. So when I have alpha equals beta, r equals 0, we have total transmission. So that angle in particular is known as Brewster's angle. Brewster's angle. And that angle has a very simple expression. Tangent theta I is approximately equal to n2 divided by n1. So here we have all these special cases observed from Fresnel's equations. So now in order to prove that we calculated the right r and t, we need to prove that there is conservation of energy. So we need to calculate the intensity of all the waves. So for oblique incidence, we only calculate the power that strikes the surface. So for the intensity I, the incident wave, we have 1 over 2 epsilon 1 v1, and then E0 squared, and then cosine theta I. For the reflected wave, we have IR equals to 1 by 2 epsilon 1 v1 and then R squared is 0 squared. So we have the R that represents a percentage of the amplitude that goes to the reflected wave, and then cosine theta R. So theta R is going to be equal to theta I. And thirdly, we have I t equals 1 by 2, and then epsilon 2 v2, and then t squared e 0 squared cosine theta t. So now we are ready to calculate the reflection coefficient. We have R equals IR divided by II. So this divides this. We have R squared. So we have alpha minus beta squared divided by alpha plus beta squared. And then for the transmission coefficients, I have t equals IT divided by II. So this divided by this. So we have epsilon 2 v2, and then t squared, and then cosine theta t divided by epsilon 1 v1, and then cosine theta I. So actually this gives us alpha, this gives us beta, and this gives us alpha. We actually have alpha beta t squared. So this equals, you cannot see there. So we have alpha beta t squared. So this equals to 4 alpha beta divided by alpha plus beta squared. Yes. So it's easy to prove now that we have conservation of energy. It is really quite a journey. It is a long journey. But if you think about the process, there are a lot of steps. In terms of calculation, they are not that complicated. They are all linear algebra. And the Fresnel's equations really is very essential to all the optics modules and communication modules that you're going to study in second part of second year and then the third year. So if you derive all these equations by yourself, it will give you a really deep common sense, really deep memory of Fresnel's equations and its role in designing optics devices and communication devices. Okay, thanks.